Today's lesson is Chapter 5, Section 3, Properties of Logarithms. Please turn in your book to page 383, I think, and get your notes ready, and let's start into this one. So on page 383, okay, change of base is going to be something that we take a look at when we're working with our logarithmic functions. Most calculators are only going to have log buttons or ln buttons, which have base 10 and base e. So if the problem involves some other base, we're going to use a change of base formula to compute them. So what this means is if I have log base a of x, I'm going to set up a ratio of the log of x over the log of a, and then I can calculate that and get my value. For base 10, for base e, those ratios look almost identical if you take a look across the slide here. Let's play with this for a second. It says evaluate log base 2 of 12 using the change of base formula and common logs. So based on that property from our previous slide, I'm going to take the log of x over the log of a. Well, the x is 12. So I want the log of 12 over the log of a, which in this one is a 2, so log of 2. And then I'm going to compute. All right, so turn to your calculator right now, and you're going to want to punch in log 12 divided by log 2. And if you punch it in right, hopefully you see this value. If we wanted to use change of base formula and natural logarithms, almost essentially the same. But remember that natural log is ln. So when I'm setting up my ratio, don't use log again. Use ln of 12 over ln of 2. Use the ln button on your calculator to punch in this division. So ln of 12 divided by ln of 2, and you're actually going to get this 3.585 again. All right, a couple more properties that we're going to take a look at today. We're going to do things involving rewriting products, okay, logs that have a product as their x value or quotients as their x value. If we have log base a of u times v, that can be split apart with a sum. So log base a of u plus log base a of v. Same exact thing applies to the natural logs, so that's within that second star right there. Number 2 is called the quotient property. So now if x is a quotient, like you see here with u over v, that's going to be the log of u minus log of v. And again, it applies to the natural logs too. We have something also called the power property. If you have log base a of an exponent, log base of u of the n power, that n or that power can be rewritten out in front of the log statement. Applies both to the common logs as well as the natural logs. These are going to be some things that we will be using today in our examples as we are rewriting and condensing or expanding our logarithm functions. So, for example, if I had, let's see what this looks like before we get into an example. How about log base 3 of 4 squared? Okay, this would be rewritten with that exponent coming out front. See how the n was out front here in our model? So 2 log base 3 of 4 would be a way to rewrite that. All right. So checkpoint number 3 then. Page 384 says write each logarithm in terms of log 3 and log 5. All right, so what they're going to have us do is use some of these properties to rewrite one that's given in another form. So looking at that 75 in our first example on letter A, and the fact that I know that they're looking for log 3s and log 5s in there, most of you can see that that 75 would break. What if I rewrote 75 as 3 times 25? Okay, so now I've got a 3 in my product. How can I rewrite a 25 so that I'm seeing 5s? All right, so 25 we all know is a 5 squared. So I have a product inside my parenthesis there. So I can expand that by breaking it apart. So our property tells us that I can pull that apart and do log of 3 plus log of 5 squared. Okay. Now also I'm going to use one last property to finish expanding this. That power of 2 on my second half there, I'm going to drag that around in front. So leave log 3 alone, but instead of having log 5 squared, I'm going to have 2 log 5. All right, so I have rewritten my statement. I've rewritten log 75 as log 3 plus 2 log 5. All right, let's do another one. Log 9 over 125. Okay, again, I think it's going to be pretty easy to see our 3's and 5's here. What if we rewrote that as log of 3 squared over 5 cubed? Now, that's a quotient. Okay, so thinking back to our previous slide, what did we do to break apart or expand a quotient of logs? I can rewrite this as log of 3 squared minus log of 5 cubed. Again, when we're expanding, we don't leave those powers in place. So the second power, bring out front. And also the third power, bring out front of this one. And there's our expansion. Checkpoint number 4 says find the exact value of ln e to the 6th minus ln e to the 2nd without using a calculator. All right, so this one, and I think it's easier to see this because some of you are starting to recognize some of those properties. I think it's easier to see this one when I insert the base. Remember with the natural log, that base is that little e. Okay? Do you remember the property? And you could rewrite these things if you needed to. But when the base matched the, I suppose it's called the base of our x value, do you remember that the value of that function then took on the value of the exponent? So if I have ln base e of e to the 6th, the value of that thing is 6. Okay, so like that, in the second half here, I have ln, or natural log base e of e to the 2nd. Using our property from 5.2, that value is going to be 2. 6 minus 2 is 4. Okay, if you're starting to master those properties, that was a really easy problem. This one I pulled just because it's a little bit more complex, I thought. It's the exact, or the actual example number 4 from page 384 in the textbook. I just didn't know if you guys would actually go through that one, if you were going to rely solely on the checkpoint problems that I put in the video. So I decided to pull this one out and do it as well. So let's take a look at log base 5 of the cubed root of 5. Okay, think back to earlier in our section, and we reviewed this a little bit in class today. How do I rewrite that cubed root? Well, that can be rewritten as 5 to the 1/3 power, right? Okay, just like a squared root can be a 1/2 power, a cubed root is a 1/3 power. So now I can use my property again, my 5's match. I'm going to end up with y equals 1/3, or my function value is 1/3. Those of you who don't remember that property, again, you can rewrite this into exponential form and end up getting it that way too. Okay, so let me just prove that. If I'm in log form currently, so if you ever get stuck and you don't quite remember the property or recognize it, I'm in log form now. If I rewrite this in exponential form, there's my x equals a to the y, and then your 1-to-1 property can finish it out for you too. So you either get comfortable enough with the properties that you recognize them and see them for what they're worth, or you can do that rewrite to probably use your 1-to-1 property. All right, so look through example number 5 in your book. Okay, rewriting logarithmic expressions are getting a little bit bigger. So these expansions are going to involve more and more parts. 5 is a good one in the book to look at. We're going to do checkpoint 5 for the video right now. It says expand the expression log base 3 of 4x squared over the square root of y. All right, so I see a quotient. I also see a product in the numerator of that quotient. So I have a couple of different things here that I'm going to be pulling apart. So first of all, I'm going to have, for that product in the top, log base 3 of 4 plus log base 3 of x squared. And then the quotient part, remember, is the minus log function. So I'm going to have to subtract log base 3 of root y. Okay, now when we're expanding, you can't leave powers in them, and you also can't leave that square root symbol in there. So let's keep on going here. Log base 3 of 4 is pretty well done. There's no more we can do to that one. This one, that power of 2, is going to come out front. Okay, remember that the square root of y is the same thing as y to the 1/2 power. So that power is going to get pulled out front. And then we finally have everything expanded that we can. Now, just like expanding, we can also work backwards the other way and condense. Okay, so we can condense or simplify with our properties just as well as what we were doing on those previous slides to pull them apart. Look through your textbook, example number 6. The more of these you look at and practice, obviously, the better off you're going to be as far as recognizing what to do. And then we're going to go through checkpoint number 6 here together right now. All right, so inside my bracket, I have a couple of things going on, and I'm going to deal with them first. You always want to go to the inside of your parenthesis to begin a problem. So leave this alone for a sec. So that log of x plus 3 minus 2 times the log of x minus 2. This minus in here between those parts indicates to me that I'm going to have a quotient. Okay? So I'm going to deal with that first. And I'm going to rewrite those two pieces in quotient form. Now, the denominator of that quotient, or the second part of that quotient, has a 2 out front of it. So I'm going to rewrite that. Okay, in condensing, I would do that. So instead of being out front, that returns or goes to the back as the power of that expression. Oops, that doesn't look very good. Let me rewrite that. That's better. Okay, so now that stuff that was inside the bracket is rewritten. Now I need to still deal with this one outside. Okay, so again, that 2 outside of my log is going to go to the back of it as a power. So I have log of x minus 3 over log of x minus 2 squared to the second power. Okay, so the 2 from out front just became the power of 2 that you see here. All right, now, since the entire quotient, or all that other stuff, is inside the parenthesis with that power of 2, I'm going to give it to both the top and the bottom. All right, and that's the most that we can do to condense that thing and bring it back down. All right, so question number 7 leads us into an application problem. It says, where are we going to use these logarithms? Which is always a good question. We always wonder where. When you have XY data that's not linear, okay, you can find how they're related by taking the natural logarithm of each of the x and y values in your table. If these points fall on a line, you're going to be able to conclude that the values are related by an equation. All right, so if you're trying to find an equation for your model or equation for your situation, if the logs of those data points, okay, so if you find the logs of all your xy points and they end up lining up, you can write a model that looks very similar to y equals mx. Okay, so it's natural log of y equals m times the natural log of x. And m is, again, in this kind of case, going to still be a slope of that linear relationship. Let's take a peek then at the checkpoint number 7. Again, the regular example number 7 is a similar type situation. In checkpoint number 7, it says find a logarithmic equation that relates y and x for the following ordered pairs. All right, so I'm just going to put on the screen here the table that I got when I found the ln of every single xy pair up here in my data list. Okay, so my ln of x and my ln of y for every point up there turned out to be this. You can check this with your calculator as well. My y's, whoops, 1.332 and 2.0001. So these are my ordered pairs of natural log values for x and y. So plotting them over on my graph here, if I did so, I'm going to find that they more or less line up. Okay, so let's quick put these over here. Oops, that's not the right, my pen didn't quite hit where I planned. Shoot a little lower. 0, 0, 1 and roughly 2/3, 2 and 1 1/3, and whoops, sorry, this is a 3. 3.002, that looks better, and a 2. Do you see how they line up? Okay, so coming up with our model or equation for that line for our log relationships here, pick any 2 points off your table and find a slope just like you would with anything else. Okay, I'm going to just pick these 2. I'm going to use the 0, 0 and then another one. So if you remember your slope formula, y2 minus y1 over x2 minus x1, and I'm going to get roughly 0.668 over 1.006. Now, 0.668 over 1 is approximately the fraction 2/3. Okay, 66, 0.6 repeating, or 66 out of 1 or 66 out of 100 are roughly equal to 2/3. So my model then is the natural log of y is equal to my slope times x. And here'd be the equation for that model. All right, I'm a broken record, I know, and I apologize for that, but you're going to get better at these properties and getting comfortable with changing them in and out and rewriting things and being able to evaluate them if you do a lot of practice. So I did not assign problems to you for today. You're going to take it upon yourself, I hope, to practice a bunch from the book, and then ones that you don't understand we can go together and do in class.